Okay, we are recording. Let me get my slideshow up. Okay, from the current slide. Boy, everything's slow. All right, any questions from what we've done so far? And I didn't realize until I was grading the one test that's been turned in how totally convoluted some of those problems were. I looked at the problems, they seemed okay. I looked at the answers, they seemed reasonable, but I didn't know how many steps it was between question and answer. So there's at least one of those. If you make a decent effort, I'm going to give you full credit for the effort. Okay? Huh?
We can blame Cameron.
Oh yeah, absolutely. Why not? Yeah, that sounds good to me. No, he typed it, but I chose the problems because all I looked at problems were answers, and they looked reasonable. But yeah, but blame Cameron. That sounds like a great idea. You might get bonus points for that one. Okay. All right. So, section 2.6. In reality, folks, sorry to burst your bubbles, okay, but most differential equations do not fit into one of these categories that are as convoluted as they are, you're able to solve. Most of them, nowhere close, okay? A first order differential equation, dy dx equal f of xy, is a source of information. We started, actually I thought it was chapter 1, but maybe they're talking about something else, by observing how we could garner qualitative information from first order differential equations about its solutions before I even attempted to solve the equation. Then in sections 2.2 through 2.5, we examine first order differential equations analytically. That is, we develop some procedures for obtaining explicit and implicit solutions. But a differential equation can possess a solution, yet we may not be able to obtain it analytically. So to round out the picture, we're going to do what basically most in reality are going to wind up doing anyway, solving it numerically, not analytically, okay? Now, what do we mean by that? How I wish this book had some PowerPoints, because I sure can't draw these things well. But I'm almost certain we've done something like this before. Let's assume that the first order initial value problem, let me get my pen activated in black, y prime is equal to f of xy, okay? And that we have initial value y at some x0 value we know to be y0, okay? So let's assume that does have a solution, okay? Now, what could we do? Well, right off the top, if you know that y prime is equal to some function, now that may be some really hairy, nasty, mean function that you can't solve analytically, but it's still a function. And if you can plug in an x and plug in a y, you get an answer, right? Well, here they give you an initial value. At x0, the y is y0, right? Right? Okay. So, plug in x0 here, y0 there. Those are just numbers, whatever they happen to be. Plug them in and get what f is. Well, that's the derivative, the slope of the curve that goes through this point, x0, y0. So you can draw a little arrow right there, okay, indicating the slope. You can have the magnitude, direction, all that kind of stuff. That's the slope, okay? Now, not really direction, but yeah, magnitude. But you know which way, by the sign of it, you know which way it's heading. Okay? Now, go to another nearby point. Plug that in. Maybe change the x a little and leave the y the same. So let's back up on x0 a little bit and leave y the same. Plug that in, see what you get there. Leave x0 the same, change y a little bit. Go points on either side. Get the same, especially in the direction of that curve. You know, you knew this was, so if this pointed up here, maybe go x of 0 plus 1, y of 0 plus 1, or something like that. X of 0 plus 1, y of 0 minus 1, you know, if it's going like this. You know, just pick another point nearby and see where it goes from there. Plug in those values into your function. You know, mean and ugly as it might be, you can still figure out what the value is. That's the slope there. Well, that may be less negative, more positive, you know, it could be whatever. So draw your various curves there. I mean, slopes there, you know, indicating what could be the direction and the magnitude, sort of where things are heading there. Okay? Now, you've got a book online, you've got a book that you don't, right? Really, I can't draw these well, so let me just give you a picture of what that's going to look like. Okay, there's what I have here. Pick some values here, okay? Here's one. This is the x0, y0, say, okay? And you know that the slope is up this way from there. So get it to align with that. You know it's coming from somewhere back down here, so pick another point here, another one here. You know, pick these points. You know, the real good, easy to calculate points, like they have on x, -2, -1, 0, 1, and 2. On y, 1, 2, 3, 4, and 5. Okay? For those points there, that's a lot of evaluation, you get your slopes. Sometimes they're horizontal or nearly horizontal. Sometimes they're very steep. Sometimes they may be going down. This doesn't show any going down. This one would have one. So draw in a bunch of those, and then the initial condition that you happen to know, start from there and try to link them together. You haven't solved it, but you have an idea what that solution curve looks like. Okay? That's what they're talking about. Now, here's some examples of that. Okay. Here's a y prime. dy dx, by the way, is equal to 0.1 times the square root of y plus 0.4 x squared. And you know that y of 2 is equal to 4. There's your initial, or some condition. Okay? Now, can we solve this by any of the methods we've done so far? What's the title of this chapter? First order differential equations. That is the first order. Okay? But most of what we've done so far have been separation of variables. You can't do that because you got that plus in there. If that was multiplied, no sweat. Okay? Plus, can't do that by that. Then we had a bunch of linear. This isn't linear because it has a square root. And I think we just about exhausted everything else we knew because, yeah, can't do it with any technique we have so far. Okay? So what we're going to do is start with the value there. Okay? Okay. So nonlinear differential equation, initial value problem cannot be solved directly by any of the methods considered in 2.2, 2.4, or 2.5. Okay? Nevertheless, I don't know why they left off 2.3. Maybe it could be worked there. I don't know. Nevertheless, we can still find approximate numerical values of the unknown x, y as a function of x. Specifically, suppose we wish to know something of the value of y at 2.5. Okay? We already know y at 2. We want to know y at 2.5. That's what we're more interested in, y at 2.5. Okay? We don't know for sure, but we're wondering. The initial value problem has a solution, we're assuming that's true, and the flow in the direction of the field in a differential equation, and that's what I was showing you in the table down here, that chart. So let's start with this and say y prime at 2 is equal to 0.1 times the square root of your y, 0, which is 4. That's going to be 2, plus 0.4 times x squared. X is 2, so that's 4. Okay? So your y prime at 2 is 0.2 plus 1.6, right? See what we're doing? Just plugging in the 2, 4 for the x, y's. You see it? Okay. We're told y, when x is 2, y is 4. That's what that tells us. Okay? So go to your y prime. We're going to calculate y prime at 2. Okay? So that will be 0.1 times the square root of 4, right? Plus 0.4 times 2 squared, right? So this is 0.2 plus 1.6, right? Okay, that's what we're going to go for. We're going to estimate this. We know this. This we know, because there's our equation. We know that y is equal to x equal to, y is equal to 4. We know that, right? So this gives us y prime at 2 is equal to 1.8. That's going to be the slope as you go from change of y over change of x, right? Well, here we have a change of x of 0.5. So if the slope here is 1.8, okay, then this is delta y, this is dy over dx, right, is 1.8. We just calculated that, right? You could change that to be change of y over change of x is about 1.8. At that point, it's exactly that, right? So now we'll do a change of y is equal to 1.8 times the change of x. By that, write it in differential form, so to speak, right? But what's your change of x? From 2 to 2.5, that is change of y is approximately 1.8 times 0.5, because that's the difference in your x's here, right? Difference in x, that would be delta y is approximately 0.9, right? Half of 1.8, right? Well, your y here was 4, and it went up by, okay, wait just a second. Say that again. Okay, your x's are changing from 2 to 2.5. This is what we're looking for. Okay, so your x changed from 2 to 2.5, that's the difference of 0.5, right? Change of x went from 2 to 2.5. this is approximate. This isn't exact, but it gives us a ballpark, right? And then multiply the 1.8, which we got from here, by the 0.5, and that gives us 0.9. So your y has changed by 0.9. Well, it was 4. So now we estimate this, that this is approximately 4.9. Okay? Now that may be a really good approximation. It may not be such a good approximation, but it is approximation. It's the general direction that's going. Okay? And then if you wanted to try it again, you could, and creep along and go another 0.5 and see where it's going from there. But what you would do first is then plug the 2.5 in here and 4.9 here and keep going and keep, that would adjust your y prime sum, might get bigger or smaller, I don't know, and then go back and do this kind of thing again and creep along and see what direction you think that curve's heading in. And it's not going to be a bad approximation. It won't be probably exact, but it's probably going to be the best you can do in a given situation. Okay? Now, if you really wanted to creep along, you could have had your delta x to be 0.001. And then do enough steps doing this every time, coming back and feeding in again, and going back through loop after loop after loop, and stepped up to 2.001, 2.002, 2.003, all the way up to 2.5. That would be a lot smaller bits, but you would probably be a lot more precise in getting there. Every time feeding back in and calculating new derivatives and new slopes and new delta, I'm not suggesting you do that. You have computers that can do that, okay? But that's how they solve them numerically, is by actually doing finite difference or finite, they have another name for it, models, okay? And it may not be exact, but it will give you at least approximate solutions, reasonable solutions, okay? Now, this statement that we just did here okay, I can't find it. Okay, let's go back and say the slope was 1.8, okay. Y is equal L of x, and the L of x will be 1.8x, and they say plus 0.04. Now, where did they get the plus 0.04? 0.4, I'm sorry, 0.4. Wow, for the life of me, I can't see.
It's in the original problem, but I don't know how it got.
Oh.
It says in
Okay, I know what they did. They did a delta x, they did an x of 1. Now, why they chose an x of 1, let's see, is there a reason for that? When it says in the neighborhood of 2, I guess they just took 1 to be in the neighborhood of 2. So they just did. But you see, yeah. Oh. No. Okay. it looks like what they're doing is sort of like what I was saying, but not quite. They jumped, rather than doing 0.5, they jumped because they seem to have forgotten about what they said earlier. In fact, I don't even see where it is now. Oh yeah, there it is. So we wish to know the value of y of 2.5. They seem to have forgotten that's what they were about. So they didn't do that. They did a y of 1, x of 1. So they were going to y of 3, and then they put a 1 there that's 1.8, add that to the 4. Okay. It is a bit strange, but it's what they're doing. Rather than choosing a delta x of 0.5, they use a delta x of 4, of 1. Change of y per change of x. Change of x of 1. So, what that produced was, from down here, from this equation, they said L of x, this is a linearization of x, is equal to 1.8x. We know where they got that. Slope, and then the y-intercept. I've yet to figure out where they came up with the 0.4. Like you say, it's in this original equation, but that's a y prime. It's not y. So that's what it seems like they may have been using. And that's what I'm trying to. Okay, if they let this be that, let's say y minus y1 is equal to 1.8 times x minus x1. Let's just say that that's what they're using. And let's go on and plug back in our 2 and 4 here. 4 here and 2 there. Let's see what that gives us. That'd be y minus 4 is equal to 1.8 times x minus 2. That'd be y minus 4 is equal to 1.8 x minus 3.6, right? Add 4 to both sides. That's how they got it. And they get y is equal to 1.8 x plus 0.4. Okay. Fine. Okay, good. They took that point and this slope and came up with a linear equation. Okay? And then what it becomes is equal to 1.8x plus 0.4. And they did it from the slope-intercept form. No, not slope-intercept, point slope form. Okay? Now, okay, what they're going to do next is use this linearization approximation to try to creep toward 2.5 by, say, 0.1 at a time. Okay? So if you put a 0.1 in here, then your 1.8 times 0.1 would be 0.18 plus 0.14. I mean 0.4. Okay? So that would be 0.58. Okay? So your y is then 0.58. Okay? And then creep again and do the same linearization and do another 0.1. That gives you the 2. That got you to 2.1. Then you do 2.2. Then you do 2.3. But every time then, your previous y becomes your last y. I mean your next y becomes your last y, and you creep forward from that one. Okay, and that's what they're suggesting that you do here. So L of 2.1, say, is equal to 1.8 times 2.1 plus 0.4. And if you got a calculator, plug that in and see what you get. What do you get for L of 2.1? It's going to be a little bit greater than 4, but not much. You got a calculator? Say again? 4.18. Okay. So that's your new y. So plug this x and that y into your equation here. Okay. So your delta y over delta x, you plug that y in, this x in, and that gives you your y prime. Then do it again. This time your, let's see, what we'll use is the delta x then. Probably a 0.4 that time, because we used the 0.5 this time. You're up to 2.1, so to get to 2.5, you use a 0.4. And you can do it over and over. The thing is, you don't have to do this. I mean, you might do it for exercises a few times, but after a while, get a computer to do it. Run your loops and set up your program. And Nigel back here has had computer science 251, and so he can set up anything and do it, right? So you do that. So there was your L of 2.1. And you can keep doing that until you get up to 2.5 and see what your value is there. Are you going to be right on the money? Probably not. Are you going to be close enough within change? Yes. So not just on the money. So this sort of gives us an idea of where to go. Let's now approach, oh, hit the wrong key, sorry about that. Let's now go to Euler's method. Man, this guy Euler, he's been around, hasn't he? Remember, he's the one that came up with the base of the natural number system. What do we call that? E. Guess why? Named after Euler. He came up with that thing, okay? He all the other things he's done. He was probably ranked right up with Newton and Archimedes, maybe the third greatest mathematician who ever lived, okay? Incredible character. So here's his method. To generalize the problem procedure just illustrated, we use the linearization of the unknown solution of y of x up in that first equation. I wish I hadn't erased it now, at x equal x0, okay? And that was L of x is equal to y0. Now we got that from y minus y0, that's where that y0 comes from, plus f prime at xy, that was that 1.8 we got, remember? I'm sorry, x0, y0, our initial points, times x minus x0. That's what we wound up doing, getting that first equation. Okay? Now, the graph of that linearization is a straight line tangent to the graph of y is equal to y of x at the point x0, y0. Now, we'll let h be a positive increment, h greater than 0, okay, of the x-axis is shown in figure 2.6, okay? Here again, sorry, I guess I could draw this, but let me put it up here. All right, here's your function. That's the solution curve we're trying to get. Here's our x0, y0. In that problem up there, it was 2, 4. 2, 4, okay? Now, your slope here was what we calculated, alpha xy. I think that was 1.8, wasn't it? Okay? At that point. And then we got an equation of the tangent line. We found out the y-intercept was 0.4 back here. Had nothing to do with the 0.4 that was up here, but it was a good guess. Okay? Now, we want to head to up here. Maybe this was 2.5, and want to find out what that value is. Well, certainly that won't get us there. That gets us over here to x1, y1, okay? It's going to be off by a bit. That's called the error between the actual value and our estimated value from plugging it into our equation, okay? So, what we do then, next thing we do is estimate L at another point, x1. Goodness, staring into that bright light is really hurting my eyes. That's equal to your y0 that we had before, plus f prime, I'm sorry, I put an f prime in here, but it was just an f because your y prime was f, not f. Yeah, okay, so that's not an f either. Okay. Now what we'll do here is x0, y0 again. I can't write. Okay. Clean that up just a little bit. Okay. Times, this time it's x0 plus h minus x0. That makes no sense at all. Okay. Where did that come from? x1 is equal to x0 plus h. Okay. Now what we're doing, folks, is this. We're letting the x increase by a little bit. You know, that's what I said we were going to do. Creep forward on the x. Moving toward that 2.5, but do it a little bit at a time. So if we did that, your next estimate here of L of x1 is going to be y0 from there plus alpha of x0, y0 from there. That's your derivative, by the way. Okay? And then here your x1 is going to replace your x, and it's x0 plus h minus x0. So that's just h. Okay? So this is y0 plus h times f of x0, y0. Okay? Where h is just an incremental value. Okay. Now, if you let this be y1 is equal to y0 plus h times f of x0, y0. Okay? No. Okay. The way they're doing things, see, in my mind, up here we should have put an x1 here, and I started to do it, and I changed back because they put x0. This, I think, is supposed to be a 1. You plug in the x1 that you get here into f here, and that'll be here and here, here and here. Okay? So y1 is going to be, here's your x1, plug that into your f, that gives you your new slope, and that gives you that. Okay. This is the formula they have at the bottom. Now, if you'll notice here, on the first half of that, they put alpha of x0, y0. Second half, they put alpha of x1, y1. I think it should have been alpha of x1, y1 all the way along. Okay? Where did you get your y1? Your y1 was this. Okay? So, okay. All right. I'm going to go back and call that zeros again. Because you see, obviously you can't put in y1 till you calculated it. So you use y0, alpha of x0, y0, and then h. That gives you your y1. Then plug this back in, and that gives you your new estimate. So it looks like to me there's two y1s. To me, this should be a y2 then. I mean, I don't, I think they've got some of their subscripts wrong, but I can't figure out, they're not consistent enough for me to tell, okay? But y2 would then be y1 plus h of f of x1, y1, okay? So that's your new y2. What's your new x2? Is equal to x1 plus h again, okay? So go with that and keep increasing and keep going, okay? Continue in this manner, you see that y of n plus 1 is equal to y sub n plus h times f of x sub n, y sub n. Okay. Where x sub n is equal to, whatever your x0 was plus n times h. Whatever your increment you decided on, then x1 is equal to x0 plus h, and x2 is equal to x1 plus h, and x3 is equal to x2 plus h. You keep on going, so xn was whatever that original one was plus n times those h's. Okay, that gives you that. This gives you your y's. Y2 was the y1 plus f of x1. So keep going that way on this. It just keep feeding them in and getting a new, every time you get a new y, increase your x to x of n plus 1, and then you put that in here and here, and that gives you x of n plus 2. So you just keep increasing every time. Okay? This procedure, yes?
So it's not y1 is y2?
What's that?
So it's not y1 is y2?
Okay, it depends. Okay. This is where their nomenclature fell apart a little bit. The very first thing they did was this. Y1 is equal to y0 plus f of x0 y0 times h. So that line was correct. Okay. Now, then you do x1 is x plus h. Okay? So now you got a new x, a new y, so your y2 is this y1 plus h, whatever the increment was, f of x1 y1. You increase that to x1 y1. Okay, that gives you a new x2. A new y2. Increase your x1 by h again. In other words, x2 is x0 plus 2h. That's what that's saying. Okay, increase that by 1, and then your y3 would be y2 plus h times f of x2 y2. Okay, that's your new y3. Increase by h again. That gives you x3. So y4 would be y3 plus h times f of x3 y3. This is how you increase your x's. This is how you increase your y's. And you just step along, step at a time, smallest step that you choose to take. That's what I said, that could be 0.001. It might take you forever, but you could do it. That's why you use a computer. You could be 0.1 and get there a little bit faster, okay? But you won't be as precise. Okay, that's Euler's method. Because every time you choose a new x1, y1, or xn, yn, you go back to your original function that we knew was going to be that. So you're using that function, that increment, calculating those two slopes every time, and then estimating the linearization of that. So every time you're increasing, or you're coming up with a new slope, and that varies how much you're changing when you go to the next step. So you're using the original function, y prime is equal to f of xy, okay? And you're using that every time you go. All right. So let's do Euler's method in example 1. Consider the initial value problem. Y prime is equal to 0.1 times, same thing we had before, sorry about that, square root of y plus 0.4 x squared, okay? With y2, y at 2 is equal to 4, okay? Use Euler's method to obtain a solution of y of 2.5. We're looking for y 2.5, okay? Using h equals 0.1, not nearly as bad as 0.001, and then later we'll do h at 0.05. So that's going to double the number of increments we're going to have, okay? Double the amount of effort you're going to make too, okay? So, let's do our first step. So this is our, let's see, maybe I shouldn't write it here. This is our F of xy, okay? F of xy. All right. Now, and this is going to be x0 is equal to 2, y0 is equal to 4. Okay? So the first thing we're going to do is do f at x0, y0. It's going to be your first derivative. And that we've already done. That's going to be 0.1 times the square root of 4 plus 0.4 times 2 squared. Okay? And that's going to be 0.1 times 2 plus 0.4 times 4. And that's going to be 0.2 plus 1.6 equals 0.8. 1.8. I can't add. Okay. Okay. That's equal to 1.8. There's your F of x0, y0. Okay. From that, we'll do y1. y1 is equal to y0 plus, what's our h? 0.1 times f of x0, y0 okay, so your x1 is going to be 2.1, right? x02 plus h, right? Your y1 is going to be, your y0 was 4 plus this, and the f of x0 was 1.8. Okay, so your y1 is equal to 0.18, right? 0.18. 4.18. We had done that before. Yeah. Yeah, 0.1 times that. Okay. Now, you got your x1, y1, so your y2 is going to be y1, 4.18, plus 0.1 times f of, I need to read, 2.1, comma, 4.18. Okay? Well, you got to figure out what that is. That is 0.1 times the square root of 4.18 plus 0.4, 0.4 times 2.1 squared. Oh, what a joy. But you've got calculators, use them, okay? Poke that in, see what you get.
So which one would be?
What's that?
Which side would be solved? Both sides, right? Or just one side?
Okay.
We solving the y2 4.18 plus 0.1 f times.
Okay. This thing right here, f of 2.1 from here, 4.18 from there. Okay? That there. We're going to, that's your f of xy, so it's 0.1 times this. Say it again?
So you just plug that into the original problem.
Yes, exactly. That thing right up there. That's what I did here. 0.1 times the square root of 4.18 plus 0.4 times 2.1 squared. Calculate that for me. Just the F part. Just the F part. What do you get? Okay. I bet you it's a little bit more than 4.18, isn't it? I'm sorry. A little bit more than 1.8.
Okay, now we're talking.
Yeah, 1.8.
It's 1.96.
1.96.
You haven't noticed that.
1.96. Okay? So you take this, say again?
Go ahead.
Now, what were you saying?
I was just saying, I got the whole thing.
You got it? Okay, yeah. When you do 4.18 plus 0.1 times 1.96, that would be 4.37. Second? 68. So that's your new Y2. Your X2 is going to be 2.2, right? Add another point H to it. Say that again now. You see where you got this? Okay. Then you multiply that by 0.1, that gives you 0.196, right? Add that to 4.18. So that's a 4.3768, yeah. I don't know where the 8 comes from. Matt, where'd you get that?
I just plugged.
Oh, you use more digits. Is that
So
right?
I just chopped in the whole.
Right, yeah, okay. You rounded, didn't you? No, you didn't. Okay. 0.1 times this is 0.196. Add a 0.196 to this, now see a 0.376. I don't know where the last 8 comes from.
I mean, I got more digits after that.
Oh, you did?
Yeah,
Okay.
yeah.
Because you didn't round, you rounded this. You had to have, right? That didn't come out
I
exactly.
just typed the same
Huh?
exact, I typed the same exact way that's on the board.
Okay. But your calculator may be rounding to 2 digits.
Okay.
I think that's what it is. You used all of them, right? So you got this, okay. All right. Okay, so that should have been 4.377 in my book, but that's fine. We'll leave those digits. Then you jump this up another one. Then you plug this into here again, except you plug this in here, this in there, do that calculation again. That gives you that. When you get an answer there, probably a little bit more than 1.96, then you multiply that by 0.1, 0.01, add it to that, and keep trucking. Okay?
You put the X2 2.2 into the, what do you plug that into?
Into the equation.
Okay. Yeah, you plug in 2.2 here and through 4.3768 here. And do that again. You come up with a different number. Multiply that by 0.1, add it to this again. Okay? And you keep creeping up. Okay? And that gives you your Y3. And then you do X3 is 2.3. Keep doing it again until you get to 2.5 and see what Y5 would be. Okay? When you get there, you have estimated it. Okay? Now, they show in the book 2 was 4. We knew that. That was original. 2.1 was 4.18. We had that. 2.2 was 4.3768, exactly what Matt got. And then you do 2.3 and you get 4.5914. Just increase that a little bit, increase, okay? Then you do 2.4 and 4.8244, and finally 2.5 would be 5.0768. Now, I get a little suspicious because your increments are increasing each time because you're adding a bigger number to it, multiply 0.01 to a bigger number, and they're sort of swelling up pretty fast, okay? But if we had gone back and used the 0.05, then what we would have is your y1 would have been your y0, which is 4, plus 0.05 here. You have to change that to 0.05 times, and then you'd have to calculate and see what f of x0, y0 was, plugging in there. But now, that 0.1 doesn't change. That's part of that problem. You know, all that remains the same. And that comes out 1.8 again, okay? But then rather than multiplying by 0.1, the 1.8 is multiplied by 0.05. So that's a smaller increment. So this next step is much smaller than this. In fact, is it a 4.09? That's exactly what it is, because you increase by half that amount. So your y1 is 4.09, and your x1 is 2.05. You see? That's increased by your new h, okay? And then your y2 is going to be this 4.09 now, plus 0.05 times f of 2.05, 4.09, okay? Which means you plug, now this 0.1 stays, that doesn't change. This is 4.09, this is 0.4, that's from there, times 2.05 squared. So that's going to be a slightly bigger number that you're adding to this, so that's going to be considerably less than that. And that gave you a 4.1842, which is interesting because now you're at 4.1. And here you were at 4.1, here you're at 4.18, now you're at 4.1842. So this is actually going up a little bit greater, okay? Then you go up another 0.05, go to the process again, another 0.05, now you're up to 4.2, and that gives you 4.3854 as opposed to 4.3768. So it actually is increasing you a little bit faster. Then you go up another 0.05, and then another 0.05, and that gets you up to 2.3, which gets you to 4.6045. 2.3 before was 4.5914. So you're still a little bit ahead. Go up by another 0.05 and another 0.05, and you're up to 2.40, which is 4.8423, and above it was 4.8244. You go up by another 0.05 and another 0.05. That gets you up to 2.50, which has you to 5.0997, whereas before you were 5.0768. You know what? That 2.5 is looking suspiciously like 5.1 to me, because that's awfully close to 5.1. Okay? So, I don't know that it's 5.1. It just looks really suspicious, like it's really, really close to 5.1. Okay? Now, I skipped a lot of steps, but you see the general process. Now, what makes this problem, and I really hate they did this, they had a 0.1 in your original problem that was in the problem. And then they gave you h of 0.1, and that's so easy to confuse with that. This is your h, that 0.1 is in your original problem. Don't get them confused, okay? The next example is example 2. And let's see how far we can get in example 2. This is one we know how to solve. We definitely know how to. Any questions before I lose this? Okay. So let's do example 2. Consider the initial value problem y prime is equal to 0.2 xy, where y of 1 is equal to 1. Use Euler's method to obtain an approximation to y of 1.5. Okay? That means some steps there, and we'll use h of 0.1 and then 0.05, just like we did before. Could have written this off to the side. I don't know why I didn't. Okay. So this is your f of xy. Okay? So your y sub n plus 1 is going to be y sub n. I say n and write 0. I don't know where that came from. Okay. Y sub n plus h times f of x sub n y sub n. Goodness, that's hard. Oh wait. Okay. Which is y sub n plus, and your alpha of that is 0.2 x sub n, y sub n. Okay? So, your x0 is equal to 1, y0 is equal to 1. That's from your initial conditions, right? Okay. So let's get trucking. You're going to do y1 is equal to y0, which is 1, plus 0.1 times f of 1, 1. Okay? So that's 0.2. Because x is 1 and y is 1, right? Okay. What's that? Okay. y1 is y0, which is 1, plus h, which is 0.1, times f of x0, y0. Whoa, right here. That's 0.2, 1, 1, times 1, times 1. So that's 0.2. Okay? So your y1 is equal to 1 plus 0.02. By that, which is 1.02. That's your y1. Your x1 is 1.1. Buy it? Okay. Let's do y2. Is y1, which is 1.02, plus 0.2 times x1 is 1.1 times y1 is 1.02. Rapid calculators, calculate. Your 1.02 from here plus the 0.2 from there times 1.1 from there and 1.02 from there.
1.2444.
1.2444. Okay? Y3, x2 is equal to 1.2, right? Okay. Y3 is 1.2444 plus 0.2 times 1.2 times 1.2444. Calculators, calculate.
Okay, so for you got x2 equal 1.2. What did you add 1.1 plus
Say it
0.1?
again.
That's like
To get x2,
uh-huh.
add another h to x1.
So you get 1.1 plus 0.1.
Yeah.
Okay.
1.2. Calculate.
1.543056.
1.53.
43056.
56. Okay. Y4 is equal to 1.543056. You got that on there, you don't have to change anything. Plus 0.2 times 1. X3 is equal to 1.3. Okay? 1.3 times 1.543056. I hope I got that all. Equal, yuck. Okay. Equal. And this is where a memory key comes in real handy. Okay, never mind, go ahead. 1.9. There are probably some other digits there. I'll do dot, and you leave them dotted on your thing, put that in memory, and then do Y5 is equal to, and by the way, X4 is equal to 1.4. Okay, so Y5 is equal to 1.9 dot, you got it in there, keep it, plus 0.2 times 1.4 times 1.9 dot, whatever you have there in your memory. Now, whoa. Oh, wait. Something seems to be dreadfully wrong here. Okay, we got the 1.02. I thought that next one took way too big a jump. Let's go back to Y2 and recalculate. I'm sorry. 1.02 plus 0.2 times 1.1 times 1.02. What do you get? Okay, they didn't. Okay, I don't have a calculator with me. I don't know if I can get my phone to work.
Yeah, I get the same thing.
Okay. They get 1.045, blah, blah, blah. Where have we messed up?
I got it. We're calculating Y2.
Y2.
I got 1.0425.
Yeah, that's what they get.
And I did 1.02 plus
No, that's
0.1.
a 0 point. Isn't it 0.2?
1.02.
Yeah, 1.02 is what we had here.
Okay.
Plus 0.2 times 1.1 times 1.02.
See, I got it. You wrote it a little different. I got 0.1 times 0.2 times 1.1 times 1.02.
Okay, say that one more time.
1.02
Right,
plus 0.1
right,
times 0.2
right.
times 1.1 times 1.02.
Oh, that's where we messed up. I forgot my H in there. How'd you let me do that? This has a 0.1 in it. The H, I forgot to put that in there. That's where it messed up. Okay. Every one of those should have a 0.1. Of course, all these numbers change big time. Yeah, that's where it was. The 0.1 is missing. That's the H. Before the 0.2. Always a 0.1 in there. I thought those numbers were way too big. That was way too big a jump every time. Okay. Sorry about that, but we've run out of time, haven't we? Okay, yeah. And then you go back and do the same thing, but instead of the 0.1s that we left off, you put in 0.05s. Okay. And that's Euler's method. Okay. And we actually know the value for this because we can actually do the equation. In fact, we did before. I just don't know where to start on the next one. But if you go way back, I think in section 2.2, I believe it was, we actually did this one, and we got y is equal to e to the 0.1 times x squared minus 1.
So like, what should it have been again?
What's that again?
It should have been 1.1.
Yeah, you have a 0.1 in front of every one of those. I'll put it here. Yeah, we were off by a factor of 10 on every one of those. Because you had a 0.1, 0.1, 0.1. But all these, that number changed, this one changed, that 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 one changed. Everything changed from then on. I was going to say, those numbers are getting way too big, way too fast. This had a 0.1 in front of it. Okay. Every one of those did. And then we can compare that to the actual y, which we got from there, just plugging in those various x's.
So the X's are right.
What's that?
I said X's are right.
Yeah, x's were fine. It's the y's we left off that factor 0.1, and that's what messed it up. Good catch. All right. We'll pick up next time in a caveat. Okay. Now, by the way, Euler would be a decent paper topic if you haven't already chosen a paper topic. We'll run into a couple more next time. And we will finish 2.6 next time. And then hopefully next time I'll have your second test ready. So it'd be nice to have your first test. Got yours already, thank you. But try to get the second. The rest of you get those in. All right, good deal, thank you. All right, all here who are normally here don't know about Antonisha or Charles.
Are you going to your office?
Yeah.
I need you to open up me to be able to register online, because when I switched over to degree plans,
Oh,
it took away
okay.
my ability to.
Okay, am I still listed as your
Yes, sir.
advisor? Okay. I can do it even if I'm not, but I have to do it a different way if I'm not. So, all right. So let me close this off.